area, I have to multiply the segment by 1. And this is not indicated there because it's just unit. So if you compute this difference here, you get basically the base of the rectangle, which is equal to the area because the height of the rectangle is 1. And 0 is of course excluded because this is a positive quantity and therefore it's greater than 0. So the maximum is indeed given by this difference.
I understand how the equations are set up, but if you look at the rainfall event in time,
Yeah.
then isn't ER2 the first contribution to runoff?
There is, if you look at the rainfall event in time, I mean, we are looking at the delta time. So, if I will understand your question, we are looking at the time C star, at the time where we have C star, and then we have at that time one given rainfall. And I don't understand your question. So, you said the rainfall event in time, what do you mean exactly?
What I mean is, yeah, so from if the rainfall event starts,
Yeah.
then the first contribution to runoff is that not determined by ER2?
Yeah, correct. It's determined by ER2.
Then why is that not the first contribution?
Uh,
Is that the second?
Yeah, okay, so your question is just related to these indexes 1 and 2.
Yeah.
Yeah, okay, I understand. They are not related to timing. It's
Okay.
just a first contribution and a second contribution. Yeah, I agree with you. Probably it would be better to call them the other way around, probably. But it's, they are not related to time. It's just, this is, year 1 is contribution of the saturated catchment, and year 2 is, the literature, when the model was presented, they adopted this symbol. But I think it would be also probably clearer if one used something like Q and not ER. But they used this symbology. I think they wanted to make clear that this is not a discharge, it's a delta volume. And because here it applies the same reasoning that I made before. If you want discharge, you have to divide by the time step. But also you have to take into account one thing, that this is represented in this way. I'm not talking about the symbols. The symbols, of course, one can take whatever symbols one wants. But the contribution is computed in this way because this lends itself to an easy algorithmic translation. So it's very easy, basically, because you also may say, why do you compute this contribution before saturation? Because here there is a maximum, and the maximum is this max operator is intended to avoid that before saturation you compute any contribution ER1, because if this difference becomes negative, it means that the catchment is not saturated and you shouldn't compute it. So one question by you could be, why do you mention this max? You could simply say that this applies only from saturation on. And the reason why instead is presented in this way is that you need to write an algorithm in R which computes for every situation the contribution to the surface runoff. And therefore you have to set up an automatic discrimination between saturation, unsaturation, and mixed situation. And by using this max operator, this allows you to easily combine. You always have to apply two relationships, year 1 and year 2, and they apply, if they are written in this way, they apply to any possible situation. And when you will see the code is indeed very simple. It's something like 20 instructions. And it is simple because it has been conceived in this way to be easy to apply. Okay, let's assume that now we know to compute the contribution to surface runoff, and now there is a question that is still open, which is evapotranspiration, because this model has the potential to take evapotranspiration into account. And look, evapotranspiration is something that you may ignore because it makes things a bit more complicated. Not really in the numerical development, because if you resolve models by using a numerical approach, it doesn't change much. It doesn't become more complicated if you add evapotranspiration. But for instance, if we consider the linear reservoir you can resolve the model analytically. And conversely, if you add evapotranspiration, it's not possible anymore to resolve it analytically. So, evapotranspiration in general is a complication, and it was a tougher complication in the past because people tried to resolve models analytically. And this is why the literature still suggests that evapotranspiration can be ignored and discusses the conditions under which you can ignore evapotranspiration. And basically the literature says that if you use the model to reproduce one flood event only, and therefore this is our purpose, because so far we are dealing with estimation of peak flow and design hydrograph. This is our context of application. The literature says that if you apply the model to only one flood event, you may ignore evapotranspiration. And why is that? Because first of all, usually floods are limited in time, and when you have a flood, usually you don't have a very warm temperature. So evapotranspiration is usually reduced. But again, this applies only if you run the model for a limited time. So basically, iMod, you could run it in the present form with still some further elaborations that I have to describe. But basically, you could ignore evapotranspiration if you use iMod for simulating only one event. But still, the models gives you the opportunity to compute it. And so now let's discuss how we can compute evapotranspiration and take it into account in the model. So the first question is, how can I compute evapotranspiration? And the second question is, how to take evapotranspiration into account into the model, into the algorithm for applying the model. So the first question, and first of all, let's recall, and these are concepts of basic hydrology, and therefore I'm not discussing this first premise in my notes. Let's define a reference value for evapotranspiration for a given site and time, and let's call it potential evapotranspiration. It is usually called EP at time t, and usually it is measured as a rate, so it is usually expressed in millimeters over time, millimeters per second or millimeters per hour. So the same unit as rainfall. And what does, from a physical point of view, this quantity indicates? It indicates a water loss. A water loss due to evaporation and transpiration. So remember that evaporation is the transfer of status of water from liquid to vapor from the liquid surfaces. So evaporation from rivers, from lakes, from reservoirs, from the sea. This is evaporation. And it's usually measured by using an instrument that is called evaporimeter, which simply is a pot that is placed outside, and in the morning you measure the water level, and in the evening you go there again and you measure the water level, which is decreased because of evaporation. So this is the first phenomenon. Evaporation is not very influent in the overall water balance of the catchment because the water surfaces are usually very limited. Because I define it again, it's transfer of state from liquid to gas, to vapor, of water from the liquid surfaces. And evaporation is instead very relevant when you compute the water balance for reservoirs like dams. This is very relevant, of course, because for a dam, your catchment of reference is just the lake. And then, of course, all the surface of the catchment is covered by a liquid surface. And then there is a second contribution which causes the transfer of status from water to vapor, which is transpiration. Transpiration is operated by vegetation, and it's the process by which vegetation, like trees, plants in general, take water through the roots from the soil and release water to the atmosphere under the vapor status. And this process is instead in the catchment very relevant, and it's very difficult to measure because, you know, it depends on the land use, it depends on the type of vegetation. Both of them, but let's say evaporation more than transpiration, are influenced by temperature and also the meteorology in general, like wind conditions. Wind is much influencing evaporation. So, to compute evaporation, to estimate the contribution to evaporation is relatively easy because it's easy to measure. To estimate the contribution of transpiration is much more difficult, and we don't have physical models allowing us to estimate it. Evaporation can be estimated by using artificial plots, and usually they are laboratory instruments. They are placed outside, but still they are part of labs, where basically you put the soil and everything, vegetation. You allow the vegetation to grow over a kind of pool, where in the pool you put the soil and then the vegetation, and you allow it to grow, and the pool is isolated by the soil. And the pool is equipped with instruments that allow you to measure its weight. So basically you bring into the pool the water to irrigate the vegetation, so the weight increases. You measure the weight, and then the next day, of course, you see the weight decreasing because the vegetation is taking water from the soil and releasing water to the atmosphere. And these kind of instruments are also used to measure infiltration because if they are placed outside, they can be tilted and they can receive rainfall. So people can measure rainfall, can measure the increment of weight of this kind of pool, which means infiltrated water, and can measure also the surface runoff because if the pool is equipped with gauging instruments to measure discharge, of course they can measure everything. But these are very small scale experiments. They are not very large. They can be large as this room, which is fine. They can have an height up to 3 meters. And it's already a very heavy instrumentation, but this is the type of scale that they can cover. So you understand that it's possible to measure also transpiration, but still it's quite a complicated process. And therefore, by using these few measurements and by using also some physical and empirical consideration, people developed several empirical formula to estimate the contribution of evaporation and transpiration. And through these empirical formulas, they are usually estimated together. And so the process is called evapotranspiration. But you know, this is something that doesn't exist. It doesn't exist a process that is indeed evapotranspiration. It's just the sum of two separated processes, and they are lumped because, you know, given that we apply an empirical formula, then it's easier to apply the empirical formula to a lumped process instead of separating into single physical processes which we cannot represent individually. This discussion that I'm offering to you, as I said, is a concept that is usually dealt with in basic hydrology courses. I am introducing it to you because I understand that some of you did not take basic hydrology, and therefore this information is important. On the other hand, it is not treated in my lectures, and I will not ask you any question at the exam about evapotranspiration. The only thing that I may ask you is the definition of potential evapotranspiration. And that's it, which I still have to deliver to you. So basically, as I said, empirical formulas to compute evapotranspiration, but evapotranspiration depends on several conditions. As I told you, it depends on meteorological conditions, it depends on the type of vegetation, it depends on the type of the soil. And therefore, there are several potential explaining variables that may come into play. So it's not really easy to set up an empirical formula that takes into account all of these factors. So the literature proposes several formulas. Some of them are very simple. They take just into account temperature, and that's it. And I forgot to mention some of these factors. There is also the exposition of the yield slope, because of course if it is southward, the evaporation is greater than in a northward yield slope. And also there is the solar radiation, because with the same temperature but in higher solar radiation you have more evapotranspiration. So there are some complicated formulas, and there are some simple ones. And usually we use in these applications very simple formulas because we don't have enough knowledge over the catchment and enough meteorological data to use complicated formulas. And then there is one factor influencing evapotranspiration which I didn't mention so far, which is the soil water content. Because if there is water in the soil, the plants have something to take. If the soil is dry, there is no evapotranspiration. So this is extremely important. So if you have plenty of water, you have a lot of evapotranspiration. If the soil, again, is completely dry, there is no evapotranspiration. You may have still vegetation there, because vegetation is, can resist for a while. And also vegetation can adapt. So if vegetation is given a lot of water, vegetation increases evapotranspiration because, of course, vegetation feels better and they grow up in a quicker solution. But if vegetation has a reduced amount of water, the plants are able to reduce their requirements. And this applies, the same applies to farmers. We know quite well that if you give plenty of water to farmers, they use a lot of water. If you give a reduced amount of water, they can reduce their requirement without impacting the production, the agricultural production. And this is related to the fact that even vegetation is able to adjust a little bit. So we need to refer to a situation with empirical formulas that is well defined in terms of water content. So these empirical formulas, the idea was to deliver to you an estimate of the potential evapotranspiration. What is potential evapotranspiration? It's defined as, and this is something that I may ask you, at the maximum value of evapotranspiration, then I repeat, that you have when there is plenty of water available. So, again, potential evapotranspiration is the maximum value that evapotranspiration can attain when water availability is unlimited. So potential evapotranspiration is the maximum value that evapotranspiration can attain when water availability is unlimited. Okay, so you get an estimate on this potential evapotranspiration through an empirical formula. I'm not introducing to you the empirical formulas. And you can easily find them on the web. Easily. Because they are also, I don't think it is really useful to learn them by memory. Because they are very empirical, essentially and fully empirical. Now, the potential evapotranspiration is not the actual evapotranspiration. So we need to adjust in the model this computed value of potential evapotranspiration. We need to adjust it to the actual or effective, it's called, sorry, effective evapotranspiration. How can we make this adjustment? In this way. And it's very easy. Don't be concerned by the formula because it's very easy. And basically, what is the ratio? The ratio, the rationale is, sorry, not the ratio, the rationale is, let's recall the definition of potential evapotranspiration. It occurs when you have plenty of water. So it occurs when you have the saturated catchment, when the catchment is saturated. So let's assume in I mode that if C is equal to Cmax, the effective evapotranspiration ET is equal to the potential one. And let's for now, don't look at the formula for now. Let me stress the concept. So we have to devise a formula that gives us a value of effective evapotranspiration that is equal to the potential value when C is equal to Cmax. Then a second constraint, which is very easy to understand, is that we should have effective evapotranspiration equal to 0 when C is equal to 0, when the water storage in the catchment is 0. So this formula that we have to devise should give us ET equals 0 for C equals 0, for C equal to 0. Or WT is equal to 0. And this is the second constraint. And then a simple relationship is to adopt a linear variation between the two extremes. So let me try to make a summary, a graphical summary. So this is my ET, and this is EPT. So this is the potential value. And here I have the storage, WT, which is related to C, as you know. We have a relationship that allows us to compute W depending to C. But let me use W because it's the storage over the catchment, is the total storage, so it's more representative of the catchment conditions. Okay, now my aim is now to draw a curve that represents ET. So let's start from 0, 0, and let's get to, for a value of W max, let's get to EPT. And remember that W max is equal to C max divided beta k plus 1 And then let's adopt a linear variation, a linear rate between these two extremes. This is the simplest relationship that we can think about. And this relationship is translated in analytical terms here. Because look, here we have W max at the denominator, and at the numerator we have the difference between W max minus WT. Now let's see if, first of all, this is linear. This is linear because you see that this is ET is a linear function of W. And let's see if, given that it's linear, let's see if it meets these two constraints. So let's assign to W the value of 0. So if W is 0, it disappears from here, and then we have numerator and denominator which become the same. So 1 minus 1 is 0. ET is equal indeed to 0. Perfect. Now, let's see what happens if WT is equal to the maximum value, which is equal to C max divided beta k plus 1. It means that the numerator disappears because it's W max minus W max, 0. So it remains only 1 here, and then ET is equal to EP to the potential value. So you can see that this is very simple. Look, this can be written probably in a simpler way. Could be if we wanted to write it in terms of CT. You could write it in this way: ET is equal to 1 minus CT divided C max times EPT. It's the same thing. You see that it's linear. If you take C equal to C max, it becomes, no, let me see, no, it doesn't work in this way, because if CT is equal to 0, no, it doesn't work in this way. I think it could work in this way. Let me see. Now, if you have CT equal to 0, then ET is equal to 0, and if you have CT equal to C max, ET is equal to EPT. Yeah, this could be a simpler way to write it, because I think it's more or less the same. Yeah, it should be the same. Because when CT is equal to 0, W is equal to 0, yeah, should be the same. It is the same. I would say, nevertheless, because I'm thinking about the relationship. I would say that this is similar, but it's not the same relationship. I think it's similar. We can make an attempt when we develop the exercise. We can try both. It's similar, but it's not the same. Why is that? Because this is linear in C, but the relationship between C and W is not linear. And therefore, let me see the relationship between C and W, what is. I think it is not linear, and therefore, if it is not linear, yeah, you see, this is the relationship between W and C. And you see that it's not linear because there is an exponent here. And therefore, basically, this second relationship that I brought here, it's linear in C, and it has the same extreme values. So for it gives evapotranspiration equal to 0 for W equal to 0. It gives evapotranspiration equal to the potential value for W equal to 1. But the variation on W, in this case, is not linear because it's linear in C. Doesn't change much actually because, you know, it is anyway empirical, and it doesn't change much. And what I suggest, we could make an experiment when we have the code, because it's very easy to make a change in the code, and see that the results will be different, but more or less the same. I tell you that sometimes I use this one, because it's simpler to remember and to write, and doesn't change much. But the model was originally proposed with the other relationship that it is reported in the lectures. It's clear, this discussion that I made, and keep into account that when you apply a model, you can be creative. You are not forced to follow the solution that was originally proposed by the literature. You may decide to change it, and the reasons for changing it may be technical reasons, because you think that representation is more representative for your case, or you may change it because it's simpler. For instance, one solution that you may adopt in iMod is to assume that beta k is equal to 1. This is up to you. And it is much simpler because you don't have to estimate beta k. So calibration becomes simpler. And you may decide that for your catchment is a good solution. So, as I said, when you apply these models, you can be creative. You are not forced, because these are not exact solutions. So let me make a counterexample. If you are required to apply the linear reservoir, and you introduce a nonlinear feature, then you are doing something that it's not what you have been asked to do. But if you apply iMod, you may decide that beta k is equal to 1, because you are still applying iMod. Or you may decide, if you think that it's appropriate, to compute evapotranspiration in a different way, or to neglect it. As I said, you can be creative. The only thing is that I suggest you that when you change, modify a model, you have a good reason to do that. Otherwise, it becomes not very clear what you did. But once that you are clear, transparent, and you have good reasons for what you do, you can be creative. So in this stage, we have computed evapotranspiration, the effective evapotranspiration. Now let's move to the next question. How to take it into account in iMod. The easiest way is that at each time step, once you computed the contribution to the runoff, you end up with an estimation of the contribution to runoff and an estimation of the storage into the catchment. You may remember that we always related C to the contribution of the runoff, but we never forgot W. And you may question this. You may say, why do you continuously propose us the relationships for computing W? They were not used so far. So far, I computed, as you may remember, the surface runoff depending on the shape of Fc. I computed the integral of Fc, and this is the surface runoff. And then I told you, but you have also contribution to storage. And I gave you the relationship for computing the storage. And you may have asked me, why is that? Well, I don't need the storage. It's not an interest for me. The explanation is that once that you computed at each time step the surface runoff, if you compute the storage, then you may subtract evapotranspiration from the storage. Evapotranspiration is a rate, is millimeters per hour, for instance. If you multiply it by the time step, you need an estimate of the evapotranspirated storage. And then you can update W by subtracting evapotranspiration. This is what we can do here. And you may ask me, should I subtract the evapotranspiration before computing the surface runoff, or runoff, or after computing it. This is up to you. Usually I subtract it, I don't remember in the code that I will propose to you tomorrow the sequence, but the moral of the story is that if the time step is limited, it doesn't make any difference. And in any case, it's part of the numerical approximation. So this is how evapotranspiration is computed, and therefore you will not see it here, but in the code you will see an instruction where W is updated by subtracting evapotranspiration. Look, by subtracting evapotranspiration, you can apply the model also to non-raining period. Because if you don't have rainfall, what the model does is just to reduce the storage by subtracting evapotranspiration. Okay, now you may say that we are done, we have finished. Actually, we still have something to say about IMOD. And so far we were able to compute the surface runoff. And so far, I just want to remind you, we introduced two parameters, beta K and Cmax. Now, application of the model suggests that it's better to add a module to the model for computing the transfer of runoff to the basin outlet. Because basically, so far, we have computed, let me make a scheme of a catchment. So we have computed